Hello, and welcome to the International Space Elevator Consortium. We are presenting Graphene, the last piece of the space elevator puzzle. Is it indeed? And today's presenter is Adrian Nixon, editor of the Nixine Journal. Adrian Nixon is a chartered chemist and member of the Royal Society of Chemistry by examination. He has over 20 years experience in manufacturing, industry, working as a scientist and a manager in technical service, research and development roles where he created several patents. Adrian gained an MBA and changed careers to work in international consulting, specializing in strategy and knowledge management. He is a board member of Nixine Publishing Limited, editor of the Nixine Journal, and advisory board member of the National Graphene and 2D Association in the US, and board member of ISIC. Adrian regularly speaks at industry and scientific events about the latest developments in graphene and 2D materials. And with that, I'm going to move over to Adrian's slides. And Adrian, when you see your first slide, go ahead and unmute and begin the presentation.
Thank you very much, Karen. And just wait for the slides to come up. By the way, you probably noticed while I'm waiting for the slides to come up that there's chat started already and a few questions are already being answered by some of my colleagues. So it's not just me that will be able to address some of the questions here. You've got some experts in the room too. So let's get started. Graphene, last piece of the space elevator puzzle. There's a question mark after that. I'll come back to that later. And if I forget to tell you why there's a question mark there, please do remind me about that. So, starting off, you know about me. I'm a board member of ISEC. Yeah, I'm a chemist. I know stuff. I'm the editor of the Nixine Journal, and I'm on the board of advisory board of the National Graphene Association in the USA. So thanks, Karen, for mentioning that. This is me with some of my colleagues. There's Professor Mike Maddock and Rob Wheeldon, who I see are in the call too. So hi, guys. Last year, pretty much this time last year, actually, we went to Washington, D.C., and we were briefing Senate and industry leaders and policymakers about graphene and 2D materials last year. So we had a fun time over there. That's all good stuff. And also, another part of what I do is I'm the editor of the Nixine Journal. Now, we established this in about 2017, so we're 3 years old now, and we're in our fourth volume of monthly editions. We try and be as independent as we can about the world of graphene and 2D materials. So we're producing one of these journals every month, probably somewhere between 35, 50 pages every month of activity. The pace of change in this whole area of graphene and 2D materials is astonishing. This advanced material agenda is just mushrooming at the moment, and we're struggling to keep up, to be honest. There's humongous amount out there. We are quite independent, so we don't, we survive by a subscription model, we don't take advertising, and we try and take a straight down the line approach to anything that we see out there. And we always try and explain the complex stuff in plain English and address the so what that's going on out there. So that's a little bit about the Nixine Journal. So you know a little bit about me now. I'd like to know something about all of you. So Karen, over to you.
So go ahead and submit your answer here. You don't have a submit button. Once you click that little circle, it records your response. And we'll give it just a few minutes to see where everyone is landing in the room. And I'm going to broadcast the results. And then Adrian, if you want to speak to what we have, the type of people we have in the room, it's really quite interesting.
It is. It's a broad spectrum of people. The one surprising thing is we have nobody in government or who admit to being in government. Interesting. Engineers and scientists, we've got other types of undergraduates, PhDs, graduates, business industry people as well, and a lot of people who are generally interested in space and space elevator. That's actually really helpful for me to know because that helps me pitch where this is going. Thank you, Karen. So, having understood who's in the room, this is what we're going to cover. So, I'll talk about the space elevator components, what it is, how it works. Then we'll look at the review the properties for tether materials, and I'll explain what a tether is if you're unfamiliar with the language. We'll look at the candidate materials that will possibly make the tether. And then I want to narrow down specifically on candidate materials and graphene and some of the materials around that. And I put this presentation together assuming a mixed audience, so everybody from rocket scientists all the way through to just somebody who is genuinely interested in the technology. So looking at the poll we've just had, it looks like we've got the range of people that are broadly expected. So that's pretty good. Thank you very much for participating in that. And we'll have a few more polls as we go along because we'll try and make it a little bit more interesting as well. So moving on, what are the components of the space elevator? Right, this isn't to scale. If you look closely at the Earth, you'll see it's not in its usual format. It's actually rotated on its side. I'll tell you why in a minute. The first one down at the ground is the Earth port. Then we've got the climber, which is the elevator cage, which goes up and down. We have the tether, which is a continuous piece of material that stretches from the surface of the Earth all the way out to the apex anchor. Um, and then we've also got a geostationary node, which is in geostationary orbit level. Now, um, how a space elevator roughly works is you can imagine if you have a geostationary satellite, so if you looked above where you are right now, the Earth's spinning, and the satellite would be spinning at exactly the same speed that the ground is on the Earth. So from your point of view, the thing above you um, is actually stationary in space and won't move. So the idea is if you could take a piece of material and drop it all the way down to the ground, then in theory you could connect up the ground with space, and then you would grab hold of the piece of material and then just climb up it like Jack in the Beanstalk. That's roughly how the space elevator works. Um, the dimensions of this are pretty challenging for people's thinking. So you look here, the scale of things. The diameter of the Earth is around about just over 12,000 kilometers. The tether, the scale of what the space elevator will do when it's built, is enormous. So it's 100,000 kilometers long from ground right up to the apex anchor. So this is roughly the thing I wanted to get across really is the fact that we have a piece of material, single piece of material, 100,000 kilometers long, that's 100 million meters, going all the way from space right down to the ground. That piece of material stays still, and the climber, the thing which goes up and down, grabs hold of the tether somehow, and then goes up and down, and you can get into space just like being in an elevator. So the technology is fairly straightforward. Let me just come back to why the Earth is on its side. So you would actually put this space elevator at the equator rather than the poles. And the reason for doing that is, yep, Keith, presumably only over the equator. There are some people in the audience who've calculated details. There is some magnitude where you can go a few degrees either side of the equator. But basically, if you can think about how the engineering works, it's if you've got a yo-yo or a weight on a piece of string and you are the Earth, if you can imagine now that you spin round on the spot and you hold the string out, the weight attached to the other end of the string will stretch that string out as you turn around. And so the centrifugal force is balancing the force pulling it back in again. Um, if you were to try and put that yo-yo thing above your head when you're turning around, you'll throw it up in the air, it'll just fall back on you. So that gives you an idea about some of the dynamics that are going on. So that's the reason you probably locate the space elevator tether and the structure on the equator. We'll talk more about that later. And we're not really going to talk too much about the engineering of this because there are other people in the audience who are far more qualified than me. I'm a chemist, so I know just enough about engineering to be dangerous. I want to talk a little bit more about the materials side of things. So the tether has to be strong. So this is another thing I'd like to ask you a question about. Over to you, Karen.
So go ahead and res respond to the poll here. Just from what you know right now, what do you think the tether should be made? And we have a couple of different selections here. If you have decided that other material might be the good selection, go ahead and type in chat and let us know what you think that other material is, if you have anything in mind. If you don't, and say we have to discover it, please let us know in chat as well. So we're getting a number of answers here. Just watching to make sure. I'm going to go ahead and broadcast those results right now. And we have two that didn't get any votes, Adrian, but I'll let you speak to what people are talking about for the tether material.
We have quite a well-informed audience. I'm curious about what other materials could be, and thanks for prompting people to type that into the chat, Karen. Maybe we can pick up on that later. Um, so it looks like carbon nanotubes and 2D materials, and nobody's voted for Kevlar or high tensile strength steel. Well, yeah, informed audience, that tells me. Thank you very much. So moving on. Interesting. The space elevator can be made with today's technology, except for the tether. And this is why the tether is so important. It is a continuous piece of material. It is about 100,000 kilometers long, and that's one continuous piece of material. Um, that stretches from the surface of the Earth into space, and it has to support not only the climber, but also it has to support itself, and I'll talk about that in a minute. Um, None of today's materials is strong enough or long enough really to make the tether. And so the whole project is sort of stalled at the moment. This is why the tether material stuff is so important. Let's sort of unpack that a little bit more. This will give you an idea about understanding the tether material problem. So if you imagine you're standing at the edge of an infinitely high cliff, um, then you want to sort of drop over some super strong material over the edge. So you're grabbing hold of it and then you're lowering it down. And then the problem is that as you keep on paying out the material over the edge of this infinitely high cliff, the material that's dangling there has weight, it has mass, and eventually the cable will break under its own weight under the influence of gravity. So this sort of neatly illustrates the tether problem. It's also that materials have to be both very strong and light. So the strength is measured in pascals with the, most of you will be familiar with the units, PA. Today's strong materials such as Kevlar, their strength's around about 4 gigapascals. Um, the space elevator tether requires an order of magnitude stronger material. We're looking at strengths of over 60 gigapascals and preferably up somewhere near 100 gigapascals. By the way, quick note about the slides. Everybody can have a copy of the slides afterwards. Um, you'll see at the bottom of many of the slides, I've put the references where I've actually sourced the information. So you don't have to take my word for these things. You can go and check the source yourself. So that's the tether material needs. Um, NASA looked at the space elevator about the turn of the century, and this is the 2000s, as part of their Institute for Advanced Concepts division, NIAC. They commissioned a study and gave Bradley Edwards a chunk of money to go away and actually say, do a feasibility study and once and for all tell us, is this space elevator stuff just science fiction or could it really be possible? And he went away and looked at it and examined all the components that you've seen. So we've got the earth port, we've got the tether, we've got the climber, we've got all the bits in space. And Dr. Edwards came back and said, do you know what? This actually is technically possible with today's technology, apart from one component, and that's the material you'd make the tether out of. And around the early 2000s, this is about 2002, 3, the main candidate that Bradley Edwards identified was something called carbon nanotubes. And he said, these are the materials which are probably going to be the strongest materials that we can identify. And this is the stuff you should make the tether out of. Now, since that feasibility study was published, material science has been developing a lot more now. And there are other candidate materials out there. So I want to talk to you about some of them. But I also want to talk about carbon nanotubes and look at the latest technology there too. So I'm not just here to preach about 2D materials. This explains a little bit about the science of candidate materials. So this is called an Ashby plot and was put together by Mark Haas of Cincinnati. You've got tensile strength on the vertical axis here, and we've got density along the bottom. And then you see these lines here. This is a line for aramid, which is Kevlar, around about 4 gigapascals. And these two lines here are sort of the plausible region for making um, the space elevator tether. And you can see that even the strongest materials like Kevlar aren't strong enough and light enough to make the tether out of. So we're looking for something which comes in between these two lines here. So if we overlay today's materials onto this graph, you'll see here that metals and alloys in this grey area, uh, they're very strong, but the problem is they are also very heavy, and so it pulls them down. Composites sort of reach up into this area, of which Kevlar is one or aramid is one. There's wood and ceramics and glass and all sorts of other things which just don't really make the cut on the plot. Now, if we superimpose carbon nanotubes, you can see the CNT stands for carbon nanotubes. We've got bundles and threads. This is the reason Bradley Edwards identified carbon nanotubes as being the material for the space elevator tether. They are strong enough and light enough, way, way strong enough to do the job. So that's an excellent candidate material. But now there are other materials that have started to come on the scene since Bradley Edwards did his work. The BNNT stands for boron nitride nanotubes. Then we've got something called HBN, which is hexagonal boron nitride, and graphene, and more about these shortly. So these materials are strong enough to do the job. We've got carbon nanotubes, a one-dimensional material. I'll speak about that in a minute. We've got graphene, which is a two-dimensional material, and we've got hexagonal boron nitride, or HBN, which is a 2D material. So if we just have a quick review now, have any of you changed your mind about tether materials?
So go ahead. It's the same poll in essence, but after the information that Adrian gave us, we want to see if there is a change of opinion in the room. I'm going to broadcast those results. You can continue voting, but that's interesting. And then Adrian, do you want me to pull the previous poll over for a comparison?
Yes, if you can do. Great.
Yes. All right. So as you can see, the one on the left is the one we just took, and this is the one on the one on the left. Excuse me, the one on the left is the one we took, and the one on the right is the one we asked before that information. So it does look like there is a bit of a change in the room in terms of more people thinking 2D materials would be a better selection.
That's good. At least I know everybody's awake.
Yes, definitely. All right. Well, I'll go
Right.
ahead and hide those polls so that we can get a little more to the presentation.
Excellent. Thank you. Right. Moving on. So, thanks very much for participating so far. That's good to see. Now, I've mentioned something about one-dimensional materials, two-dimensional materials. Uh, Graphene, carbon nanotubes, hexagonal boron nitride. What is all this stuff? Right. So we start up here with carbon nanotubes. Um, They are made of carbon, as the name suggests, and it's like a hexagonal lattice just wrapped up on itself, a bit like the inside of a toilet roll tube. Um, the There are no joins around the cylinder, and the material can only grow out from either end. So it can either grow out this way or it can grow out from the other end. So In terms of the number of dimensions it can grow out in, it's restricted to just one axis. So you can think of it as a one-dimensional material. Graphene, on the other hand, this chicken wire stuff here, is made of exactly the same stuff that carbon nanotubes are, and it's arranged in the same sort of way with these hexagonal lattice, except this is now just a flat sheet. Now the graphene can grow out in one of two dimensions, so it can grow out in the x direction or the y direction. It can't grow out in the z direction in terms of three dimensions because what tends to happen is it stacks. So one graphene layer stacks on top of another, and the continuous covalent bonds don't cross across the stacks under normal circumstances. So this is why it's a two-dimensional material. Hexagonal boron nitride is analogous to graphene. It is a bit like this chicken wire structure made up of hexagons, except now we've got alternating atoms of boron and nitrogen rather than just everything being carbon, as in carbon nanotubes or graphene. But again, you can see here that it's a two-dimensional material because it can grow out that way or it can grow out that way, but it can't grow out vertically. So this will give you an idea about some of the language that we're using in terms of what are the materials and a brief introduction to dimensionality. For the physicists in the audience, you'll realize that the term two-dimensional was actually applied to graphene because the way electrons move in graphene could be described with mathematics that was just in two dimensions and it didn't need the third dimension. So that was where the original 2D term came from. But for the moment, we're appropriating these dimensional terms for our own purposes. And broadly speaking, in the graphene and 2D world, people wouldn't really have a beef with that. So let's have a look at manufacturing technology and see what's been happening. We'll start with carbon nanotubes. I did actually say I was looking at carbon nanotubes as well as the other candidate material because I'd like to try and give a fair shout to all of them. This is some recent work that's been done with carbon nanotubes, making the nanotube thread. And if you were to just sort of read the title of the paper, then you would immediately think, oh, we can get carbon nanotubes which are going to be quite long, so therefore job done for the space elevator tether. However, when you actually read the paper and then start to unpack what's going on, what the team are actually doing is something slightly different from a tether perspective. So they're starting off with a feedstock. The carbon source is butanol, and then they've got ferrocene and thiophene. These are just catalysts. Which are in a hydrogen carrier gas. And you heat this up to about 1200 degrees C or so. And then you've arranged the furnace so there's a vortex. So as carbon nanotubes start to form, the vortex of the gas spins them round one another, and eventually outcome from 1 millimeter long carbon nanotubes, you end up with a long filament, which then spins and can be wound up onto a drum. That's all very good. The problem is that these individual filaments aren't connected together. They're not bonded together. They're just sort of held together by physical forces, Van der Waals forces and things like that. So what happens is that you have created a carbon nanotube fiber, but it's made up of lots of little bits. So when you put it under stress, then it tears itself apart. Interestingly, the people behind this paper didn't actually do any tensile strength tests on it when I read this. So, but we can expect it probably to be in the megapascal range. I did see some stuff that was done by another team looking at a similar technique that was done in January of this year rather than 2019. And they did claim to have low gigapascal strengths for something similar. So um, this is it's
Adrian,
still not going to be strong enough. Yes, Karen.
we have a couple of questions that I think might be a
Hmm.
good opportunity here. They have to do with basically what you're talking about. So a question
I'll move
came
on.
in, if
Sorry, Karen. I
damaged,
thought
I'm
you
assuming
needed.
if is referring to the graphene, how much can the material be repaired and can its tensile strength be
So
restored? No, can you hear me now? Adrian,
mhm.
can you hear me? Can anyone hear me?
Let's have a look. The sound was coming
Yeah,
and going
okay,
there.
so
So what has the... I can hear you
okay,
now.
so
Yes,
I'm going to
that's
read
fine.
this one. Oh, yes, I can.
So which
If
questions would you like me to
damaged,
look at?
how much can the material be
I can hear you.
repaired
Yes. Can you hear
and can
me?
its tensile strength be restored? I'm assuming they mean the graphene. And Kevin, if that's incorrect, please type in chat. And is that a question for further
Yes.
research?
That's a really, really good question because we can expect things to be damaged up in space because stuff bumps into this. There is further research, yeah. In principle, yes, there are ways of repairing the tether. That would probably take another 20 minutes to sort of unpack and go into. So probably the best thing I could say is yes, we're thinking about that, and
Right, and it was actually
I could
referring
quite
to
happily take
graphene
some of the
or
detail
carbon
offline.
nanotubes,
But in
just to be
principle,
clear
yes, it
here.
could be repaired.
Another question came in. Can graphene be developed to be intelligent? In other
Would
words,
you like another
repair
one?
itself? Or is that part of our 20-minute additional conversation?
And can you hear me? We've got a slightly flaky connection, I think, Karen. I'll try and be patient and wait for it to catch up.
So hopefully Adrian will be able to hear that. Yes, we can.
Hmm. I'll assume you guys can hear me. So just
Okay, so the
ah,
question was, can graphene be developed?
here we go, Karen. I'm back now. Yeah.
Yes, can graphene be developed to be
So was there a
intelligent? In
question there,
other words,
Karen? Because if
repair
there was,
itself.
I just missed one. Hmm. Let's think. Can graphene be intelligent? It's under tension, so can I? Yeah, I would probably say no at the minute. You'd probably have to have an outside intervention, but in
Absolutely.
principle, there are
So
ways
let's
of
move on with the
patching this
presentation.
stuff
I don't
up.
see any
Can I
other
park that again and
questions.
come back to when I talk about graphene? Great. Okay. Yeah, again, we've got a slight delay with the internet, I think, but everybody's been patient and thank you for bearing with us. So, and thank you for bearing with me too, Karen. So moving on, there's some more work done on carbon nanotube thread. This is some more work done last year. A similar sort of carbon fiber nanotube reactor, again, sort of trying to sort of get the density up to increase the bonding between the carbon nanotubes with an acid and acetone bath. They've managed to get the strength up a little bit, but again, the part of the problem with carbon nanotubes is because you can only make them in small quantities, then you can't really get the strength up because you need continuous material, not lots of little bits all stuck together. So try as I might, looking at carbon nanotube technology, at the moment, as far as I can find out, the longest nanotubes that have ever been made were made in 2013, and they're 500 millimeters long. And as far as I can work out, the work seems to have stalled on that. Nobody can really make them longer. What seems to be happening with the research is that the longer you try and make them, the more the carbon nanotubes stack up inside one another, rather than um, extend in length. And a lot of the work has moved over towards 2D materials and graphene as such. So that's pretty much that's a quick summary of where we are with carbon nanotubes. If we move on now to 2D materials, taking a quick look at hexagonal boron nitride, one of the materials was boron nitride nanotubes. These are analogous to carbon nanotubes. Um, they are out there, they're in the labs, but very little published work has been done on these. And again, I think there's a similar sort of problem, that there's a very difficult task to try and make these any longer than millimeter lengths. So at the moment, boron nitride nanotubes will probably park them for the minute. Some interesting work is taking place making small-scale HBN as a single crystal. I'll talk about single crystal a little bit later. But this is some work that was done in Korea where they've actually started to grow hexagonal boron nitride on liquid gold. And then as the hexagonal boron nitride spreads over the gold surface, then the domains lock together and we end up with a self-assembled single crystal of HBN all over the surface. This sounds great. Problem is, rather dangerous. We're dealing with molten gold at very high temperatures. It's also a slow process. Um, this is inching along, and also it's not available at large scale at the moment. So we're just talking about tiny sort of square centimeter scales for making this stuff in the laboratory. So moving on to graphene, and this is another one of those 2D materials. Now, quite a lot of you will be familiar with graphene because I suspect you're a fairly sophisticated audience, so you'll have heard of it. Um, the candidate materials, graphene isn't just one material at the minute. The commercial stuff is actually being done with graphene powders. These are made from graphite, the stuff in pencils, and then ground up into a powder and then separated out. And these things are part of the graphene hype. People expected graphene to be produced on the scale of rugs and carpets. And then they've ended up seeing these black powders, and everybody's had their expectations built up to a huge amount and then crash back down. So a lot of interest has been lost in the graphene world. Meanwhile, these graphene powders seem to have been creeping up on people. They've been used as additives in lots of different materials. And while we're not really going to talk about them too much, because that's a whole other presentation by itself, pay attention to graphene powders if you're in the advanced material world, because these things are enhancing polymer composite materials. You can get double-digit strength improvements. Add it to concrete, tiny amount of concrete, and you'll increase its strength by 25%, which if you run the numbers, you could take 2% off global CO2 just by adding a tiny amount of graphene powder into all the concrete that's made. Um, so there's great things happening with graphene powders. However, they're like little bits of graphene and they're no good for making a space elevator tether. The other thing we're interested in, really, for our purposes, is this CVD graphene, this chemical vapor deposition graphene, which makes this chicken wire mesh of two-dimensional graphene. And the term that we'll start to use now is single crystal graphene, which you need to have in your lexicon and be aware of because there's something quite important about that. Just to give you an idea about why graphene is a material that will start off a new materials revolution, then over here you can see, you can read this as well as I can, 200 times stronger than steel. It's the world's best conductor of heat and electricity, very stable. It's hang around for ages. It doesn't degrade. It won't poison you, as far as anybody else has been able to find out. Handling dusts is a bit of an issue, but that's the same for any dust. It's nothing special with graphene. Flexible and transparent. It's got an incredibly high melting point, about 5,500 degrees C. So this stuff could sit nearly on the surface of the sun and still be quite happy. It's also the world's most fatigue resistant material. If you imagine stretching this stuff over a drum and then hitting it repeatedly, you'd have to hit it really hard about 1 billion times before it failed. Incredibly strong stuff. And a few weeks ago, it was found that it's the world's most impermeable material. So researchers in Manchester have just discovered that 1 atom thick of graphene is equivalent to a kilometre thick wall of glass when it comes to holding in things like helium gas. Astonishing stuff. So this is all to do with single crystal graphene, perfect layers um, of material. And I've just seen some interesting questions appearing in the chat, which I'll come back to in a bit. So Karen, you might want to pull up on some of those in a minute. I mentioned about single crystal graphene, so just to give you a quick understanding about what this means, the picture here is cling film. I think you call it saran wrap in the States. So that's not graphene, but we can think of it like that. A crystal in this context means a repeating pattern. And when we make graphene as a single crystal, it will be like large scale sheets that you can roll up and unroll. And Graphene will be, in this context, crystal means that actually it'll be a floppy, bendable, stretchy solid, not like the crystal of everyday experience, something that shatters and breaks, but it will be transparent. So that's just to give you an idea about what we mean when we talk about single crystal graphene. It's a defect-free sheet of graphene. It's a single molecule from beginning to end. How's graphene made? Well, this is the chemical vapor deposition route. So we start off here. The graphics have just got slightly mangled, but don't worry about that. But basically what we've got here, this is methane. So we've got carbon atom in the middle. We've got 4 hydrogens attached. That bond should be linking the two together. And then normally pulling these hydrogens off the carbon is really hard to do. You might be able to get the first one off, but then the others are increasingly difficult. However, if you get methane very hot, and get the gas close to the surface of a metal such as copper, what happens then is that the hydrogens start to come off the carbon, and then the carbon lands on the surface of the metal, and the metal acts like a dating agency for the carbon atoms and then encourages them to one, sit on the surface, and two, connect up together. And you'll be familiar that when things want to connect up with one another, they do so in terms of the lowest energy shape that they can adopt, because that's how nature works. And this turns out to be this hexagonal chicken wire graphene shape. And once the surface of the copper is covered, then there is no more metal to catalyze the reaction stops, and you end up with then a 1 atom thick layer of graphene, which you can then peel off from the surface, and that's how graphene's made. And that is the chemical vapor.
All right, please stand by. Yes, we did lose Adrian. Hopefully he'll log back in.
We get to when the internet decided to
You
cut
were
me off.
just talking, yes, you were talking on the slide and
Mhm. About single making graphene on copper.
yes.
Ah,
Mhm,
right. So it was this slide I got to. Right.
mhm.
Okay. So very quickly, when I was talking about that, we've got methane here, carbon, hydrogen. The methane comes down to the surface of the copper. The metal acts as a catalyst. The carbon comes away from the hydrogen, and then the carbon joins up and covers the surface, and it adopts the lowest energy shape it can, which turns out to be the hexagonal chicken wire lattice of graphene. And then once the surface is covered, then there's no more metal exposed, so the metal can't act as a catalyst anymore, and the reaction stops. It's a self-limiting reaction. And so we end up with a 1 atom thick layer of graphene over the surface. And then once you've done that, then you peel off and remove from the copper to leave the 1 atom thick graphene sheet. So far, so good. I can see some of the questions building up here, which we'll answer in a second. So the issue here with this technique is that even if you look at down at the microscopic level, the copper or any other metal contains grain boundaries, crystal grain boundaries, which can't be removed. And these are a little bit like crazy paving. So you have gaps and chasms, and the graphene tries to grow over some of these. It can bridge some of these gaps, but it falls down some of these holes. And so you end up with defects in the graphene layer because it's growing over a defective surface. And the other problem is we get is snowflake deposition, which is that the graphene starts growing at multiple points all over the surface at the same time, and then these grow out from these points and to create domains of graphene, which then collide with one another. And again, they give you a crazy paving pattern. And wherever you have discontinuities or defects, then we have weaknesses, which then create what's called a polycrystalline material. And we need a defect-free material, which is single crystal. So hopefully you begin to get your head around the language and roughly how some of the state-of-the-art production is working at the minute. Now, this is one of the areas I work. Um, the This is what's called the geek, and when I'm there, I'm working on the second floor up here with some of my colleagues, Rob Wielden, who's in the call as well. He and I work there on a weekly basis before the lockdown. And the rest of the geek is one of the most high-tech advanced facilities in the world for researching and connecting the research with the commercial activity in the world of graphene. We're there because Nixon Publishing is an affiliate partner of the Geek, and I get to see some cool stuff. And I thought I'd like to share this with you because very few people have actually seen this. So a few months ago, we were there in December, and we got to see some CVD graphene that I've never seen before, like this. Basically, this is a sheet of graphene, a sheet of copper foil on which graphene has been grown. Now, the really interesting thing about this, and the thing that hardly anybody has ever seen before, is we've got an area down here at the edge where there's no graphene growing on the copper foil, a blank edge. And then over all this area here, we've actually got graphene covering the foil, CVD graphene. I don't know if you can see, but can you see that line coming down here? What you're actually looking at there is the boundary between graphene and copper. And what you're actually looking at on this side is a 1 atom thick layer of graphene covering the surface of the copper foil. I just think that's amazing. Hardly anybody has ever seen this before. Lots of people have been shown graphene on copper, but never that boundary. So you can actually see the difference that a 1 atom thick layer of graphene makes on the copper foil. The researchers that discovered or isolated graphene figured out that it would absorb about 2.5% of light. And that's why you can see through it. And also, it has a metallic appearance, so this is why we're getting a slightly more silvery color on than copper foil. But it really is amazing stuff. And again, you can have copies of these slides. The interesting thing is to point out here is that this is polycrystalline graphene. So remember all that crazy paving stuff? That's what you're looking at there. But the defects are so small that you can't see them with the naked eye. You'd even have problems with finding them with a microscope. There's a scale bar here showing you roughly what size things are. Anyway, that's one cool thing to show you. Moving on, we talked about single crystal graphene, and is it possible to make defect-free single crystal graphene? Rather than run a poll, I thought I'd just tell you this. The answer is yes. In 2017, in Peking University, a team started off with a piece of copper foil. Now, what they did was they made a long piece of copper foil with a pointy end and then a flat continuous bit. And what they did was they annealed the copper starting off at this point and allowed the annealing process to go all the way along the copper foil. And what they did there was create a single crystal of copper going from the pointy bit to the end bit. So there are no grain boundaries, which is quite a clever idea. So now they've made a perfect surface of copper without all those domains. They've still got the snowflake deposition problem, so they came up with another idea, which was they got the growth conditions right. So they're now creating hexagonal domains, and the other clever thing is that they are making the domains aligned so that as the domains grow, the domains actually match up and connect together seamlessly, forming a single crystal of graphene over the surface. Really clever stuff. And the other thing to note about this is, look at the scale that they were working on. This is a piece of copper, 50 millimeters by 500 millimeters. That's half a meter long. And they covered that with a single molecule of graphene. And just think about that. That is quite astonishing. The graphene that they made wasn't perfect. It was 99% close there, but they've proved with this process that you can make single crystal graphene over the surface of the copper foil. Now, interestingly, the time it took to actually cover the surface with the graphene. So to create this half a meter long single molecule took about 20 minutes. So we've got a production rate, if you like, in the laboratory of about 40 minutes to make 1 meter. Now, give you an idea about where we're going with the space elevator tether. We're looking for something which is about 100 million meters long. So if you run the numbers, we're just looking at this process. It's probably going to take somewhere in the region of about 7,500 years to make one layer of tether. And that gives you an idea about some of the challenges that we're working on here. So we're going to have to make the tether at very high speeds. We're going to start with baby steps. You've seen that we've started around about 1 meter every 40 minutes back in 2017. So Karen, over to you for another poll.
We have a poll there, so go ahead and submit your answers.
Ooh, interesting.
And I'm going to go ahead and broadcast those results. So 5 to 10 years seems to be the winner.
It does, doesn't it? And it tells me that there's nobody that has said never. So you're an optimistic lot in the audience. That's good. But I don't mind people who are critical either. Um, so we got 18%, 18, 19, yeah, I think less than a year, 5 to 10 years. Yeah, 5 to 10 years seems to be getting it. So you're an educated lot, quite well informed. Some of you are more informed than others. Thank you, Karen. We can move on. Well, a few weeks ago, and this is literally about 4 weeks ago, I was in a webinar and I was listening to a presentation by LG. You've probably heard of LG, the electronics company in Korea. Now, they're not making graphene for space elevator tether, they're making graphene for electronics. So just get that clear already. But one of the interesting things they've been doing is they've been working in secret on a process, and it was only last month that they actually released images and started talking about the process they got. You see this chap here, he's holding a copper foil. You know, look at the scale of that. That's 400 millimeters wide. This is a roll-to-roll machine, so it's a vertical furnace. So what you're looking at here is humongous amount of development work going on. The copper starts off as bare copper here, it goes through a vertical furnace where they've got the CVD technique, the CVD process going on, the chemical vapor deposition, which coats the surface of this graphene in coats the surface of the copper in graphene, and then it's rolled up again on the bottom. That's astonishing enough. The fact that they've been investing this vast amount of money just to get to this stage. But the really interesting thing that got me, look at this roll speed down here. What they've done is, as well as announcing a roll to roll process, a vertical tube furnace, they've already got a high speed process going. They're already capable of making graphene at a process speed of 1 meter a minute. I mean, that is just astonishing. I didn't believe it when I first saw it. I had to go back and double check. And that's the reason I've put LG slide up here so you can see it as well as I can. Um, the pace of development in the graphene world is astonishing. So just within um, three three years, going from the peaking work now to now, they've increased the speed that you can make graphene astonishingly well, and they've moved from the laboratory to a continuous process. The other thing is, it's not just LG that are working on this. I know of 4 other companies that have got roll-to-roll processors going, and the reason I've put LGs up here is because they've been more open than most about some of their stuff. At the Geek, where I work, then there's another one of these roll-to-roll machines in the ground floor laboratory, which is due to come online back end of this year. So a fantastic amount of work going on here. So we'll just come back again 1 second. So they're making graphene now at speed of 1 meter per minute. So if you remember the Peking University one, they made it 1 meter every 40 minutes. That would take about 7,500 years to make a piece of tether, just one layer of tether. Now at 1 meter a minute, it's only going to take 198 years at this speed. So again, you can see the challenge. Even though this is astonishingly fast, we need to be much, much faster. But what this work shows, and the reason that I'm so excited about it, is the trajectory for development. The speed limit for making graphene is limited more by engineering, there is rather than science. So we can. This is definitely pointing at the area that we can get the speeds up, and we'll be able to get the quality up as well. One other thing to mention about this is it's making polycrystalline graphene. So again, it's still not all connected up in as a single crystal. So there's still more work to be done. But hey, what can you expect in 3 years? But hopefully I've landed the production side of things with you and you're getting an idea about some of the stuff that's been going on in secret, which is starting to be announced. So, um, how do we go about building a tether from single crystal graphene? So First of all, we need to know how big a reel of single crystal graphene would be. So it's not a trivial problem. It turns out that you have to know a number of things. So we need to know what the size of the core is. We need to know how wide, what diameter of that is, and also how wide that would need to be. So if we assume we're making graphene across a meter, and let's assume we've solved the problem of single crystal and high speed, then could we physically get it up into orbit? I mean, is this how big is a reel of single crystal graphene, 100 million meters long, wound round on itself, and how much would it weigh? So I had some help on the calculations with Dr. Peter Clark. If we assume a 20 millimeter core and 100 millimeter, 1,000 millimeters wide, a meter wide, interestingly, it turns out that this distance here is just 300 millimeters, a foot across. How much would it weigh? Well, that reel would weigh 77 kilograms. Now, I don't know about you, but if we're going to get something up into orbit, then that strikes me as being not impossible to get one layer of tether up into orbit. And we're going to need to get lots more of these. But the reason for showing you this is to say this stuff is actually doable. So how would you go about doing it? Would you build it from the ground up or space down? My money's on the space down side because you really want gravity to work with you rather than having to fight it on the way up. So the basic principle is you would take the reels of single crystal graphene up into orbit, unreel them, and then connect them together, layer them together, and to form a graphitic tether. And we need to be working on tens of thousands of layers. I'll come back to that in a minute. How we'd actually go about doing it, we'd take these cassettes up into orbit, which would be like mini spacecraft by themselves, which would unreel and then pull down through pinch rolls. Now, these pinch rolls here are important because when you get graphene, and this, Gregory, this comes to your point about how do you stop graphene sheets from sticking to itself like saran wrap is, the answer is you don't. You actually want the graphene to stick together. So just like saran wrap, you can reel it onto the reel, but you'll be able to reel it off the reel as well. And when one sheet of graphene comes into contact with another, van der Waals forces will glue them together. So you don't actually need another glue. The van der Waals forces between two atoms are very weak, but graphene has a massive surface area, and a very small series of forces multiplied over a huge surface area creates a rather strong force. And while we don't know the total details about how this force will work over multiple layers, meters wide, because nobody's ever done it before, um, then the 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 indications we've got so far are that this will hold together itself by itself. If it can't, there are ways we can actually weld it together too. Peter, you just asked a question about why aren't the reels glued together in the cassette? The answer is it's like the van der Waals forces. Again, you'll have come across van der Waals forces in nature with geckos. They climb up walls with van der Waals forces on the hairs on their feet, and they're like Spider-Man. When they plant their foot onto a surface, the surface area effectively glues the gecko to the wall, but they can peel off. So just like taking saran wrap off a roll, it's very hard to get off a surface when it's stuck on it flat. But when it's on a reel, you're only peeling off a small area, and that's why it's not glued together in the cassette. It's held together, but you can unreel it as well. So that's roughly how you'd think about making a tether from orbit in principle. I'm conscious about the fact we're getting close to the end of time. So, Karen, quick question to you. Do you want to take some questions now, or shall we talk about Obayashi and run the vid?
Why don't we show the video? I know we are getting close to time. We will obviously continue the
Oh,
webinar for those
while
of you
we're
who can stay
waiting
on
for
past
Karen
the
to come
allotted
back,
time,
then
but
I'll just talk to you about the Obayashi
right, so we'll
Corporation.
go ahead and run the
Then
video here, and
Obayashi
we want to
is a
thank the
corporation,
Obayashi
large construction
Corporation who
corporation in
graciously gave
Japan.
us permission
They're one of the
to
top five,
show this video.
and they're committed to making a space elevator. They want to do it by 2050. The Chinese are also
Yes,
committed to making a space elevator, and they've got a target of 2040 to
Adrian.
actually build this thing. Other people around the world are working seriously and thinking seriously about this stuff. And good idea.
Okay, so Adrian, here is our video, and we want to thank the Obayashi Corporation for providing this and giving us permission to show it during the webinar. And I'm going to go ahead and play it. If you notice, there are some controls for your own volume on the lower right-hand corner, a slider bar that will allow you to reduce the volume if you need be. It opens at highest volume. So here we go. All right, it does seem as if the video has stopped playing for everybody, which is good. It does play at different speeds depending on your internet connection. So hopefully it is done for everyone. And it is in the recording. So I'm just going to go ahead and close this video. And again, we want to thank the Obayashi Corporation for providing us permission to view this and have it in our own webinar. As you can see on Adrian's slide here, there is a link and that will take you directly to where the video is on the internet. Yes, it did stop, Peter. It did have some, there was nothing of interest later on. It was just more information and in terms of the production. So we saw what we needed to see. Thank you for pointing that out. And Adrian, I believe you are back with
Yes,
us and
yes.
should have your phone rights.
Thankfully, it kicked me out when the video was playing, so you hopefully haven't noticed me missing too
No, we were watching the lovely video, so
much.
so
The reason I wanted to put
there
the
we go.
video in is because it sort of communicates in a nice way the sort of magnitude and the scale of what we're doing. Sometimes you can live and breathe this stuff, you can take it for granted, but it is quite astonishing technology that will get built. Do you remember at the beginning I said that there's a question mark in the title here? That's not. Don't read that as a measure of confidence. I know this can be done, and it will be done. I'll read through this summary and then I'll come back to that question mark in a minute. So hopefully what you've seen so far, been I've taken you through the space elevator components. We've looked at the properties for tether materials and why the tether is such a challenging problem and why it's the critical part of the space elevator program. Then we've looked at candidate materials, carbon nanotubes, graphene, boron nanotubes, other materials. We've looked at the latest updates on the candidate materials, all the way from graphene, carbon nanotubes, hexagonal boron, nitride. So you've seen some of the latest research that can be found on this stuff. And we found that carbon nanotubes research is effectively stalled. They can't make them long enough. Graphene seems to be the one which is in the lead at the minute, and the way that the production technology is moving at an astonishing speed. Um, we're climbing up the technology readiness levels like mad at the moment. So hopefully that's given you some update on the candidate materials, and you've also seen some insider information, which hardly anybody else has seen yet. You've seen a one-atom thick layer of graphene on copper. You've seen what some of the secret research projects and the commercial people are doing, and there's lots more other stuff I couldn't put into this. Problem is, we'd have gone on for a couple of hours. So you've seen the tip of the iceberg. There's a huge amount more work going on. Um, Coming back to that question mark, the last piece of the space elevator puzzle, there's no doubt the space elevator can be built, and therefore it will be built at some point. The question mark refers not to whether or not the space elevator can be built, but whether graphene would be the material. The main thing is we've got choices. We may have had carbon nanotubes as a choice. We may still do if somebody figures out how to make them long enough. But we've got graphene, we've got hexagonal boron nitride. Graphene isn't the only material to make the space elevator tether from, and that is the reason the question mark's there. And that comes back to some of the questions that we'll talk about perhaps briefly that have been piling up. So thank you very much for listening. Karen, thank you very much for being patient with me for disappearing in and out. Have we got time to do a few questions?
Certainly, certainly. Please go ahead. I know it is the little past the end of the time that we allotted and slated, so if you have other engagements you need to get to, don't worry. We are recording this bit of as well, and it will be in the recording for you to view at a later date, but
Would
I'm
you like me
happy
to
to
read
stay
through the
on
questions,
and
Karen?
have you go
Mhm.
through. Certainly. I think you have answered some of them. They're over there in our little presenter area, so I'll just make that a little bigger.
Yep.
So I think you've answered some of them, but others are
Okay,
just coming
so
in, and I'll paste them as we go along.
yeah. So first of all, Paul Pfister, can graphene be developed to be intelligent? Can it repair itself? The answer is probably not repair itself, but it should be repairable. We could have, because that CVD process we talked about, it's possible to run that on the tether in situ and fill in holes. So it should be possible to repair it, but we'd need some kind of repair bot to do that. Um, Again, you've asked if graphene gets hit by lightning, will it damage the attached structures? Possibly. The lightning conductor technology is fairly well known and understood, but we might also short circuit the atmosphere. The thing is, nobody's ever built something like this before. Graphene is highly electrically conductive. And do you remember I said that why the question marks there? We've got choices. The other material, hexagonal boron nitride, is just as much an insulator as graphene is a conductor of electricity. So if electrical conductivity turns out to be a problem, we've got the perfect 2D material which can actually coat the tether, or we could even make it out of it. And it would be as pretty much as strong, have some slightly different material properties, but it would protect from lightning. Gregory, how do you keep single crystal graphene sheets from sticking to itself? I've sort of covered that one already. The sheets do stick to themselves with Van der Waals forces, but you can peel them apart. And it's the peeling technology that you need to develop. And that's already quite well developed in for making things like saran wrap already. Victor Production, did they test it, the thin graphene on copper? Yes, they did. They used Raman spectroscopy, which is basically bouncing a laser off the surface. And from the returning light, you can work out not only is it graphene, but also are there any defects and how many layers there are. If you look up Raman spectroscopy and graphene on the web, you can find out a lot more there. Haven't got time to go into that at the moment. Kevin, is this single crystal and have they done it on tensile test or conductance? Right. The single crystal graphene has been made in a number of places now. The Peking people started it, the Koreans have picked up on it. They have actually managed to isolate single crystal graphene, one atom thick, and put it into a tensile tester. And they've found that it is actually 130 gigapascals intrinsic strength. So, yes, the single crystal is as strong as theory says it would be. The Young's modulus, I think, was 1 terapascal. So that just confirms it's the strongest material ever tested. Um, Gregory again, could space solar electrical power be delivered to Earth this way? Yeah, very smart. Um, we've got a conductive electrical cable going from space down to the ground. Might be possible to use that as a power cable as well. So the answer is, in principle, yes. We need to think around some of the unintended consequences there, but in principle, yes. Um, Yashurio, yeah, sorry, Yashuhiro, forgive me. Um, how can we prevent space debris impact damages on the space elevator, which is made of graphene? Afraid the space elevator could be broken into impacts, even the space debris is small. Yeah, you're quite right. Um, Space debris, I imagine Pete Swan, the president of ISEC, has covered this in some of the chat. You'll find there's plenty of material on the ISEC web, and there's also a book out, which Pete will mention, talking about this stuff. But yep, space debris will hit the tether. The tether can be moved to avoid big bits. There are plenty of small bits there. Most will bounce off the tether because the tether is incredibly strong. Some of it, we've been running calculations looking at the way that space debris impacts it, and it should survive most impacts and be repairable afterwards. Also, there's people involved with ISEC who are working on cleaning up space junk too, to remove the debris in the first place. AJ Burke, do we know what LG and others are using graphene for? Yes, we do. Um, they're using it to make electronic devices, sensors, and particularly Hall sensors. These are very sensitive magnetic devices. That's what they're making it for, but there'll be lots of other applications too. Peter, would the space elevator material manufacturing be funded by terrestrial applications? That's a cracking question. Yes, is the big answer. In on the way to making space elevator tether quality graphene, you're making the most advanced material in the world at high speed and big scale, and that means cheap. So you've now got a world-changing advanced material that is going to be making a space elevator tether, but it can be used for all sorts of things. So if you can imagine layer this stuff up on a small scale, and less than a meter, you could have something which is as thin as cling film, and it would stop a bullet. Um, just think about the applications of that one alone. We haven't got time to talk about terrestrial applications. They are in the hundreds of billions. Um, Victor Production, did they test 100 by 500 millimeter single crystal? They didn't test it on that scale. I think it was much smaller, square millimeter size, as far as I'm aware. But the one to look at is Rodney Ruoff's lab in South Korea has done the testing there. And Steve Rogers, how has LG addressed high-speed extraction of the polycrystalline graphene from copper? Excellent question, Steve. Having made the graphene, how do you get it off the copper? The answer is with difficulty and maintaining the quality. There are two ways of doing this. One is to stick something which is sticky onto the graphene surface and then peel it off and then get it off the sticky stuff. The other way is you dissolve the copper from underneath, leaving the high quality graphene there. And LG, as far as I'm aware, are working on both of these. So yes, that's another part of the production process which is slowing them down. The reason I put the LG process in is because it shows how quick you can make graphene in the first place. And that is a really important step to know. We know there isn't a speed limit for making graphene. Pierre, for small and light payloads, um, is a small geospace elevator demonstrator possible with actual tether material? Yes, clever question. In making space elevator tether, what you would do is you'd make it like a bridge. So you send a small rope across first, and then use that to pull a bigger one, and that to pull a bigger one, and so on until you eventually end up with a bridge. It was probably similar construction method for the space elevator. So you'd start off with maybe uh, a few hundred layers, perhaps, and then you would build a construction space elevator tether which would haul the rest of the material up into space. And then, so effectively, you have a small space elevator tether that then makes a big one next to it, and then you carry on building. Keith, will we test around the moon or asteroids being mined first? Good question. You could build a space elevator tether with Kevlar on the moon. It's been shown, and some of the guys in the chat we know more about this. Um, the problem is you've got to get out of Earth's gravity well first, so you've got to overcome the expensive bit of getting out of Earth, and that is a really difficult challenge. So I'd say build the Earth space elevator first, then look at the moon and asteroids. But definitely you could use them for mining outer space. Mavi, hello Mavi. Since our graphene is powder, yes, you do make powdered graphene. How could it be used and be a part of this? Good question. Your graphene is turbostratic graphene. It's made by an environmentally friendly process. So I think from memory, you're CO2 negative. So we'll probably need things like advanced composites to make the climate and other parts out of. And the environmental considerations would be quite an important part of this. And ISEC has a program looking at this. So chances are we probably would want to use graphene powder in some of the composites, not only from an environmental perspective, but also lightweighting and strength too. And finally, Victor, will high energy particles damage it? Really good question. Out in space, we've got cosmic rays and things like that. We've also got atomic oxygen, very reactive corrosive species up there. So yes, the answer is it will damage it, but these will be sort of small impacts which should be repairable. And the guys I'm working with are already thinking in terms of having repair bots and crawlers which would actually resurface the tether and repair it on the fly. So yes, you're right. High energy particles will damage it, but it'd be very small and point damages, which could be repaired. And can you join two graphene sheets end to end by overlapping them? Yes, you can, David. Um, but they will tend to slide over one another. So you'd need to, if you if you have two graphene sheets joined in the middle, let's say they overlap by a meter or so, you could probably grab hold of either end and give it a strong tug, and probably my guess is you wouldn't be able to pull them apart laterally, but if you got a strong enough force, you would be able to. So you couldn't make the space elevator tether out of lots of overlapping sheets. My guess is you will need a single crystal going all the way from the ground right out. But there are ways that graphene sheets could be welded together. So in principle, yes, you can join two graphene sheets end to end by overlapping them, but probably not to make the tether out of. But you can make all sorts of other useful things. How are we doing?
Whew. I think that is the end of the questions right now. And as promised, down underneath your chat pod, I put the PDF of Adrian's presentation here. So feel free to download it. Just click on that name, download the file. A separate browser window will open, and then you will be able to save that file to your computer. So for this webinar, I'd like to thank Adrian Nixon for putting together this great webinar for us on graphene and answering some questions and so forth. And there is a couple of questions there in chat, Adrian, so when I get done, you may look at those and perhaps answer them.
Mm-hmm.
I want to encourage everyone to stay in touch with the ISEC. You can go to www.isec.org. If you hover over that link is clickable. It will take you to our website. Make sure you scroll down on that home page and you can sign up for our newsletter, which we send out monthly. Please consider becoming a part of the ISEC family with your yearly membership. We have very, very, very reasonable membership rates. As you can see here, everything is in US dollars. That Join Now button here, go ahead and click that. That will take you right to the page that you need to fill out in order to join our group. And we are talking about member-only events online, as well as perhaps offering some other member-only perks. So please consider joining. Our next webinar, my goodness, you can't see that. That's if you go to www.isec.org/events, you will see when we will have our next webinar. We are talking about having a next webinar in July, in the middle of the month. So make sure you check back to isec.org/events to see when that exact date is, as we are preparing that right now for you. And then finally, I do want to call attention to our sponsors for this webinar. And I want to thank Adobe Connect, who is actually providing us the platform for this particular event that we're using, and not as well as the Learning Guild, who is also providing us the ability to use the platform. And then I'm your webinar producer, Karen Gleason. All of those are clickable if you'd like to learn more about any of our sponsors for today. And with that, I'll turn it back over to Adrian. So there were a couple of questions, I think, Adrian, as I started off. Let me go back here. From Kevin, how much friction does the material have for the purposes of attaching a climber?
That is a really good question. Graphene is a fairly slippery material. So if you tried to sort of grab hold of it, it could potentially sort of slide around a bit. But remember that I talked about Van der Waals forces being, they sort of multiply up over a large area. If you have something like a wheel gripping the tether, so two wheels, one on either side, and the tether would sort of be a flat ribbon-like structure, then there's a relatively small contact area between the wheel and the tether itself. So potentially it could slide around a little bit. But if you have something which is more like a tank track, where you've got a greater contact area between the moving bit and the tether, and also it would peel on and peel off, you've got a better chance of gripping it and holding on. There are plenty of other. In fact, there are people in the chat who are specialising in exactly these sorts of problems at the minute. It's an active area of research. And once we start getting enough big pieces of graphene to get hold of and overlap them and layer them up, we can actually start looking and seeing if the theory actually matches up to practice. And there are already climber competitions that have been going on around the world for a number of years. So, really good question.
And with that, I think that ends our webinar. All the questions have been answered. Please visit isec.org to learn more. There is a wealth of information about the space elevator on our website, so please do visit and consider becoming a member. Thank you so much for spending your time with us, whether it be morning, afternoon, or evening. I know we have a global audience, so thank you so much, and have a good rest of your particular day, and have a very nice weekend. We'll see you next time. Bye-bye.
And thank you to everybody as well. Bye bye.